Hi and welcome back. We know that if we apply the Laplace transform to a linear ordinary differential equation, we will obtain an algebraic equation. And hopefully we will be able to solve such algebraic equations. So we apply the Laplace transform, and then the plan of course is to apply the inverse Laplace transform to undo it so that we can solve such differential equations. So this diagram here explains this interplay between the time domain and the complex frequency S domain. Now if we have a linear differential equation, this looks like that. Where we have n up to an n order derivative on the state variable x and up to an m order derivative on the input variable. And typically in actual physical systems this m is smaller than, and I'll explain why I'm mentioning this. So we have this equation over here, and we know that if we apply the Laplace transform, say on the derivative of x over here, so if we have the Laplace of x dot, then this is equal to so we have this expression here, but it is minus x at 0 plus, which is a constant. And we have a similar formula for the second order derivative. Where again we have the initial conditions over here at time 0 plus. Now if we make an assumption at this point, if we say that all initial conditions of this differential equation are equal to 0, this means that if we assume that x at 0 plus is equal to 0 and x dot at 0 plus. So if we assume that all derivatives up to order n minus 1 are equal to 0, then we can eliminate these terms. We can simplify these expressions. So the Laplace transform of x dot is s times x of s uppercase, by the way, is the Laplace transform of x lowercase. Then the Laplace transform of the second derivative is s squared times x. The Laplace transform of the third derivative is s third, s cubed times x, and so on and so forth. And the same, of course, holds for the input variables. So if we assume that all derivatives of the value of u at 0 plus and all derivatives of u at 0 plus up to order m minus 1 are equal to 0 at time 0, then we can eliminate the constant terms we have over here. So the Laplace transform of u dot is s times u uppercase. The Laplace transform of the second derivative is s squared u, s third u, and so on and so forth. So if we apply this rule now on all derivatives, we will have that by application of the Laplace transform on all terms of this equation and taking into account the assumption that we have 0 initial conditions, then we have a0 x uppercase plus, so x dot becomes s times x dot, x double dot becomes s squared s, and so on. And the last term here is an s to the n power times x, and we see we have x here everywhere. So this is equal, now the right hand side becomes b0u plus b1, and again on the right hand side we have u everywhere. So we can collect x and u respectively, and this equation can be written equivalently as follows. So we have a polynomial times x is equal to a polynomial times u. And now we will do the following trick. We will rearrange the terms and we will define x over u to be a function of s. Let's write it down first. So x over u is equal to the following. X over u in the S domain is defined by this function where the numerator, it is a fraction where the numerator is a polynomial of degree m and the denominator is a polynomial of degree n. So this is a rational function. Then we have assumed that the numerator has a properly smaller degree than that of the denominator. So this is called a strictly proper rational function. Can you see it over there? Yeah, okay. And one thing we know about such functions is that we know how to determine their inverse Laplace transform, all right? Now this function that establishes essentially a relationship between the input variable u and the state variable or output variable x is called the transfer function of the system. Now the thing is that if we have the transfer function of a dynamical system, of a linear dynamical system, which is described of course by a linear ordinary differential equation, we have the same information as if we have the original ordinary differential equation. And we can do many things with this transfer function. So before we proceed, let me underline here that when we have a transfer function g of s, which is typically a strictly proper rational function, then we can draw the following thing over here. We can treat the dynamical system we have as a black box with an input u and an output x. And if we have this transfer function, we can write that x is equal to g times u, which, unlike differential equations, is a very, very simple expression, right? But this is done, of course, provided that two very important assumptions hold. And the first one is that we have a linear dynamical system, and the second is that we have zero initial conditions, all right? So provided that these conditions hold, we can write our system like that. This is an expression that explains the dynamic relationship between u and x. You can plug here any input you like, and you can simulate the system and produce an output x of s in the S domain. And then if you like, you can apply the inverse Laplace transform and obtain the output in the t domain. So you start from a u of t in the time domain, you apply the Laplace transform, and you use the transfer function to obtain an S domain response of the system. And then you undo the Laplace transform, and you have simulated your system. So this is all pretty nice and neat and easy. And it obviates all the mathematical drudgery of solving differential equations, which is the whole point in using the Laplace transform. Now let's give a very short example. We have an RLC circuit which is like that, a resistor, inductor, and capacitor over here. And we know that we can derive that. Actually, we will not do it now, but it's very easy to derive the equation that describes this circuit, that describes how V in produces V out. So we're looking here, the objective is to determine a transfer function G, which explains precisely this dynamic relationship between V in and V out. And G of S is defined as V out divided by V in. in the S domain. So we can derive the following integral differential equation that describes this system, and the equation is the following. So it is V in is 1 over RC times the integral plus V out plus L over R times the derivative, the time derivative of V out. In this first equation, in this first line, these are all functions of time, so V out of time here, right? So if we apply now the Laplace transform, and we assume 0 initial conditions, we have the following. So now these are all functions of the complex variable S. And now the next step is to collect all V out of S on the right hand side. This function inside the parentheses is a rational function indeed, although it's not entirely clear because we have different denominators. So this is the denominator 1, this is R, and this is RCS. But we can multiply the second fraction by RCS. And we can multiply the last fraction by CS. We can multiply the numerator and denominator. So we'll have here LCS squared. And then this becomes So it is indeed a rational function. By rearranging the terms, we have obtained this very simple expression. We have RCS in the numerator and a second degree polynomial in the denominator. Indeed, it is a strictly proper rational function, and we can do all sorts of things now with this function. Let's call this g of s first of all. We can do all sorts of things with this rational function. For example, we can ask what happens if the input is the Dirac function. So what is then the output? We can ask what happens if the input is equal to 1. What is then the output? 1, by the way, is often written as follows: h0 of t, the Heaviside function at time 0. And we can also ask what happens if the input signal in the time domain, again, is a sine function. We can again ask what is the output. And these three questions have names. The first one is called the impulse response of the system. The second one is the step response. And the last one, this response is the frequency response. And we can answer all these three questions using the transfer function of the dynamical system. So the transfer function gives a lot of information, gives actually all information that we need to know about the linear dynamical system with 0 initial conditions. So we are saying that the input-output dynamic relationship of a linear dynamical system that is described either by a linear ODE or a linear IDE with 0 initial conditions can be described nicely and neatly and simply using such an easy equation. X equals g times u, where g is the transfer function of the dynamical system. So we're talking about a black box with an input u and an output x and a function g in between, which describes how the S-domain signal u produces an S-domain signal x. Of course, if we have a time domain signal u lowercase in time, then we can apply the Laplace transform to determine the S-domain signal U uppercase. And by that, if we produce an S-domain signal X uppercase, we can apply the inverse Laplace transform L inverse to determine the time domain response of the system. And there are three important responses that we mentioned previously, and these are, first of all, the impulse response, which is the response of the system when u of t is equal to delta of t, the Dirac function. And then delta produces the Laplace signal u equals 1. If u lowercase is delta, then the Laplace transform of delta is 1, and then x becomes g times u, right? But u is equal to 1, so x becomes equal to g. And then the response of the system then will be the inverse Laplace transform of g uppercase. Let's write it down here. X of t is the inverse Laplace transform of g uppercase. Let's give this a name. Let's call this g lowercase of t. Let us denote the impulse response of a dynamical system by g lowercase. Now the second case is the step response. What happens if u of t is equal to 1? Or sometimes you will see this written like that. What happens if u of t is the Heaviside function with parameter 0? This means that there was a switch, the input is determined, the value of the input is determined by a switch, so that at time 0 it's off, and then suddenly it goes straight to 1. So in that case, if u of t is equal to 1 or h0, then the S-domain signal that corresponds to u, if we apply the Laplace transform here, we will get 1 over s. And then x is of course equal to g times u, so g times 1 over s, or just g over s. And x of t is the inverse Laplace transform of g of s over s. The important observation here is that we said that g of s is typically a strictly proper rational function. If you divide it by s, it remains a strictly proper rational function, and we know how to determine the inverse Laplace transform of that. And one important, an additional observation is that here we introduce a pole at 0. So this becomes a strictly proper rational function with a pole at 0. Now, of course, g of s might have itself a pole at 0. So this function g divided by s has at least one pole at 0. All right? So x of t in that case is the inverse Laplace transform of g of s divided by s. There is a third case, and the third case is the frequency response. Now the frequency response is what happens if u of t is a sine function of omega times t. Now look, if u of t is sine of omega t, then u uppercase, the Laplace transform of that, is omega divided by s squared plus omega squared. X uppercase here is g times u, so g times omega divided by s squared plus omega squared, and this is the inverse Laplace transform of g omega divided by s squared plus omega squared. For all it's worth, if you like, you can note here that omega is just a scalar multiplier, and since the inverse Laplace transform is a linear transform, we can move that outside the transform. So if you like, you can write it like that. And this is again a strictly proper rational function, and we know how to determine the inverse Laplace transform of such functions. Just note here that for sure plus minus j omega is a pair of complex conjugate poles. In fact, it's a pair of imaginary conjugate poles, and we know how to proceed and determine the inverse Laplace transform in such a case. But in general, look now what happens. In general, when we have an input u of t, then we said we obtain here the input in the S domain, so u of S is the Laplace transform of u of t. Then the output of the system is g times u, and x of t is the inverse Laplace transform of g times u. This is the inverse Laplace transform of the product of two functions. And we know from the convolution theorem that this is the inverse Laplace transform of the first function, convolution with the inverse Laplace transform of the second function. But the first term looks familiar. What is it? It is the impulse response of the system, so this is g. And what about the second one, the inverse Laplace of u? This is u lowercase. What a great result here, because this interprets the transfer function actually as a convolution in some way. So to produce a response, to have a response as a result of a particular input function in the S domain is equivalent to determining the convolution of the input with the impulse response of the system. In other words, if we have g, we know everything about the system. We can determine any response of the system given zero initial conditions, If we have g, if we have the impulse response of the system, again we can determine the whole dynamic behavior of the system. We know everything that is to be known about that system. So this much about transfer functions. Now, transfer functions are nice things because unlike differential equations, they are very easy to work with. So when we have a system with a transfer function g, we can tell that the output of the system x in the S domain always is g times u. Now this very, very simple observation and this very simple framework allows us to compose multiple such dynamical systems with one another. Essentially, we're saying that any physical system or engineering system can be understood or can be encoded as a black box with an input and an output. For example, this here can be a circuit, and the output of a circuit, which can be either a current or a voltage or some other quantity, can be an input to another dynamical system, can be a quantity that affects the dynamics of some other system. So you can have a circuit that controls a motor. So this can be G1, let's call this G1. And we can have here another transfer function, G2. This can be a circuit. This can be a motor. This can be a robotic arm, and so on and so forth. So the output of a system is the input to another dynamical system. So this is X1, goes into G2, produces X2, goes into G3, produces X3, and so on and so forth. But we can study each dynamical system individually and then compose them all together. How is that? We have X1 is G1 times U, then X2 is G2 times X1, X3 is G3 times X2, all right? And we can go here and we can observe that X2 is G2 times X1. This implies that X2 is G2 times X1, but X1 is G1 times U. So this function, G1 times G2, let's call it function 1, 2, is a transfer function that describes the relationship between U and X2. So if we want to see what happens as we change U, if we want to see what is the output X2 of that dynamical system that comprises two individual dynamical systems, then we have that the total, the overall transfer function is precisely G1 times G2. And there we have X3 is G3 times X2, which is G3 G2, G1 times U. So when we have three transfer functions connected like that in series, this is a series connection, then the overall transfer function is G1 times G2 times G3. Let me write it here. And I will say it again, this is a very neat and nice and elegant way of studying dynamical systems because it allows us to model systems individually. We can take laws of physics or laws of chemistry, of circuits and so on, and derive these different components, these different dynamical systems, and then we can compose them like that if the output of one system is the input to another system, which is very, very common in engineering. But in control theory in particular, we have one more way of connecting different dynamical systems. And we have discussed a little about that briefly in the past. We're talking about feedback loops, where we have here a dynamical system with transfer function G, let's say G1, and it has an output X and input signal U. And what we often have to do is that we take that output and we plug it into a dynamical system G2, which has an output. Let's call that Z, for example. And then, sorry, actually, we have an input over here. We take Z and we compute the difference between U and Z. We denote that like this typically, a plus here, a minus here. So U comes in from this direction, Z comes in from that direction, and we produce U minus Z, which is fed into the system with transfer function G1, and the output of the system is X equals G1 times the input, so G1 times U minus Z. But look what happens here. Note here we have X. X goes inside here. So Z, the output of this system, is Z equals G2 times X, right? Because this is X. G2 times X equals Z. So let's write there. G2 times X instead of Z. And now this describes a relationship between U and X. This equation describes how the input U here affects the output X. Let's make it clearer. So we see here that this is by definition the transfer function between U and X. Let's write it down once again clearly. We have a dynamical system with input U and output variable X. We're talking about this system, and this system has the transfer function G1 divided by 1 over G1 1 plus G1 G2. Now look here, we have a minus here, and this minus becomes a plus. I will write it in red because this is important. We have a minus here, and this minus becomes a plus. If we had the plus, that would become naturally a minus. But in most cases, in control engineering, we have negative feedback loops. So the two important things that we need to keep from this discussion is the series connection that we discussed about previously and the feedback connection that we described just now. So as you go from the input to the output, you meet G1 and you write G1 here in the numerator, and then if you notice here we have a loop, a feedback loop that involves G1, G2. So you write G1, G2. It is the plus sign because we have a minus, this becomes a plus, and it is 1 plus G1, G2. Now if G1 and G2 are rational functions, then naturally this whole thing is again a rational function. Eventually, if you need for any reason to take the inverse Laplace transform on this function or to determine the impulse step or frequency responses of this system, you know very well how to do it using what we discussed about the inverse Laplace transform. Now let's make it clear, the reason why we're discussing these things is that the typical feedback loop in an engineering system looks like that. You have your system here, let's call it G system, okay, which is described by a transfer function. Then this system is actuated using an actuator. this is often treated as an additional component, as a separate component of the dynamical system. If you have a system of tanks, this will be a valve. If you have a robot, this will be a motor, most likely, and so on and so forth. So you have the actuator here, which has itself a transfer function, is described by a transfer function, g-act, actuator, all right? And here someone has to manipulate that actuator. If you have a car and the actuator is the steering wheel, someone has to take a decision about how to steer the car. And this is now the controller. And you guessed right, this has its own transfer function. Now the controller takes the control error and produces a control action. To see that, this is the output of the system. The output of the system is measured using a sensor. With transfer function g sensor, and the measurement, let's call this xm as in measurement, is subtracted by the desired value, which is called a set point. So here we have the control error plus minus. So at that point we have the control error, which is equal to x set point minus x measured. And this is a feedback loop. Now if we need to determine the transfer function that describes the relationship between the set point and the output, we have to use what we just discussed. So the series connection, you see here, 1, 2, 3 systems are connected in series. So the controller, the actuator, and the system can be described by a single transfer function, which is g controller times g actuator times g of the system. And this describes the relationship between this signal over here, the control error, let's call this E, and the output of the system, X. So these three functions can be described by a single transfer function like that. To be very clear, these three green blocks are described by this green block. And now this red block we can draw here underneath. And this is now the second connection that we discussed about. This is a feedback connection. So if we need the relationship between the set point, which is an input variable, and x uppercase, which is an output variable, we need to write simply that the output divided by the input, so the total transfer function that describes this system is, we said before, as we go from the input to the output, we meet this function, the green one. Let's write here g controller times g actuator times g system, and in the denominator we put 1. We have a minus here, we have a minus here, we have a minus, so minus becomes a plus, and then it is the product of the two functions that we have in the loop. So it is g controller times g actuator times g of the system times g of the sensor. Now this function has a particular name. It's called the closed loop transfer function, g CL of S. This has the name closed loop transfer function. And it allows us now, if we have this function, we can determine the impulse response of the closed loop system. What happens if you apply an impulse here? What will be the output? What happens if you have a step change? From 0 you go to 1. If this is the Heaviside function, what is the output? This is the step response. And another interesting response here will be if you have a sine function as input, what is the output function? What is the response of the system? And this is called the frequency response of the system. So this much about transfer functions. In the next video we will talk about some particular type of transfer functions which are very useful in the study of circuits. We will introduce the concept of impedance, which is it will facilitate the analysis of circuits tremendously. So this much about transfer functions. This is all you have to know about transfer functions. Thank you very much for watching, and goodbye.